Okay, thank you for joining back. So we have a lot to cover today. I would keep on asking you to join and rejoin because actually we have a lot to do. Okay, all right, so this was where we stopped. Okay, so we define we define some variables as single, then we define some as double, then we we set the parameters. This is for single precision, and obviously we already know it's going to give us an error because single precision is limited. When you set for single precision, at the end of the day, this one is going to be lost because it only represents a limited number of decimal points. But when you do for double precision, this one is going to be captured. So you are going to see that. And also this one too is going to be captured. So we are going to get a more accurate result. Okay. Then this is for the double precision. Then we get the root x11. So x11 is for the double precision. So this is the first root plus, then the minus is the second root. Then this XLR is using the second equation we derived. Remember I said there are two equations. So this was the first one, but this is like the second one in order to reduce the effect of subtractive cancellation. Then you are going to display the result. So this is why it's a subroutine. For a subroutine, you just, since you are not going to call the function within the Excel program, since you are not calling the function within the Excel program, then you're going to display the results. You are left to display the result because a subroutine is, you're not going to call it, so it's just better you display the result. So this is saying that in sheet 1 of the Excel, you go to B2, cell B2, then display X1. So X1 was the result we calculated here. So display the result of the calculation in B2. So B2 will give us, is going to have the value of the first root. Then offset by 1. This represents the row, and this represents the column. So go to the next row, then write the value of x2. Then this is saying go to the next, not if it was 1 0, it's going to the next row, but offset by 2 rows. So go to leave a row empty, then go to the next row, then write the value of x11, then go to the next row, write the value of x22, then offset by 2, offset the row by 2, then write the value of XLR. So this is it. Then let me go to Excel and share. This is the function we have. Okay. And it's not capturing it. So let me go back to, okay, I think there's a question. Go to movie 1. Okay, thank you. Thank you for that. Okay, so this is the code. Okay, so this is the code for the subroutine. So like I said, this is a subroutine. So you don't need to call it in in you don't need to go to Excel and call it. So this is the Excel sheet. This is the Excel sheet. So what you're saying is that you should write the value of x1 in B2, then go to the next row, write the value of x2, then skip a row, then write the value of x11. So this is actually x11. Then go to the next row and write the value of x22. Then skip a row because we don't want it to write it here. So we offset by 2. Then write the value of XLR. So this is what we are going to do. So this is a subroutine. We're not going to call it. We're just going to leave it like this. Then when I click on run, I'll go to the Excel VBA. So this is the Excel VBA. This is the Excel VBA. Then when I click on, because it's a subroutine, all I just need to click is run. Once I click on run, the values are going to be displayed on the Excel sheet. So that's the difference between a function and Excel and a subroutine, a sub. So I'll just click on run here. So once I click on run, so it runs the program. Then I will go back to Excel. Then the results are going to be displayed just like you said it should be displayed. So it displays x1 in B2, x2, it goes to the next row, it skips this, goes to the next row, and displays it. So this was when we used the single precision. This was the root we got. Obviously, there's an error here because we know that the exact root is 0.01. Then when we use the double precision, the error was minimal. So we don't, because like I explained, double precision it makes the error to be much smaller because it captures much more decimal places than single precision. Then this was when we used the modified formula and we got the exact root. So this demonstration is to uh, explain errors in the concept is to explain errors in the concept of single precision and double precision. So we are going to write another function in Excel, and it's going to be a subroutine. And the subroutine is to calculate the exponential of x, where x is given. So x is given in the question. But what this program actually does, because there's a difference between that program and the first program we wrote to get the exponential. So what this program does is that it's going to be displaying the terms as we do it, as we calculate it. So it's going to, for the first term, it's going to display the first term and it's going to display the solution. Then for the second term, it's going to calculate it and display the solution. For the third term, it's going to calculate it and display the solution. Let me just go back to Excel so that you would understand. But before I actually do that, remember that I just want to show you something. Remember that for this one, we used sheet 1. For this one, we used sheet 1. We use sheet 1. Then for this one, we are going to be using sheet 2. So sheet 2 here. So let me go back to Excel so that you can see what I'm saying. So I'm in Excel now. Okay, so we use sheet 1 for the root. So we are now in sheet 2. Okay. So this is sheet 2. So what I'm just trying to say is that you can, and this is sheet 3. Instead of opening another Excel book and saving it as a new name, you can just use the sheet function and just say that, okay, define a subroutine and say that, okay, display the result of this subroutine in sheet 1. Then in sheet 2, you write another subroutine, then display the result in sheet 2. Then in sheet 3, you can do that. You can keep on creating more sheets, sheet 4, sheet 5, sheet 6. So this, let me delete this because I don't actually need it. Okay, so this is going to use sheet 2 and display the result. So let me run it. Let me go back to the Visual Basic and and run it. Okay, so this was the first function to calculate the root, and we're using sheet 1. So this is sheet 1. So this is the second subroutine. I'm using sheet 2. So I don't need to open another Visual Basic application and write another subroutine again. I don't need to do that. So that's why I'm just trying to tell you that I'm using sheet 2. Then let me run it. I want to, sorry, you may not hear me clearly because rain is falling. So I'll try to increase my voice. Okay, so this is sheet 2. Let me run it. So once it runs, then I will go back. Once it finishes, I'll go back to sheet 2. So if you see the sheet 2, you will see the output of the program. You will see the output of the program. So what the program does is that it takes the content of B1, then it's calculating the exponential of what is in B1, and in this case, it's calculating the exponential of 10. So it starts with the 0th term. It's because we're using the Maclaurin series. So this is the first term, which is 1. It now gets to the second term, which is 2. It calculates that particular term. So this is the first term is 1. The second term is x. So x is 10. So you have 10 here. The third term, when you are on 2, is x raised to power 2 divided by 2 factorial. So when you do the calculation, you get 50. What you have here is x raised to power of 3 divided by 3 factorial. You get this. So it keeps going to the fourth, fifth term, then calculating it. Then for this is the sum. So it calculates the sum of the exponential of the infinite series. This is the first 0th term. This is the fourth term, first term. This is the second term, third term, and everything. For this sum, it calculates 1 plus 10, that's 11. 11 plus 50, 61. 61 plus 166, that's 277. So I'm just, I want you to first of all see the results before I explain the code. So let me go back to the code. So here is the code for the subroutine. So you define some parameters, some variables. 10 represents the summation. Let me go back to the notes to explain it. Okay, so 10 is the summation up to the up to the prior to the specific term you want to calculate. For instance, if you calculate this sum, the sum is equal to the summation of this. So this is the sum. But the term is equal to the summation from this point. So the term and the sum, they are almost the same thing, but the term is just one term away from the summation of the current iteration you are on. That's the difference. Then you have test. Test is a variable that defines the current iteration. So this will give you the zeroth iteration. This is the first iteration, the second iteration. So it's going to calculate this value. It's going to calculate this value. Then sum, I've explained it. Then x is actually the exponential of what you want to calculate. Then I is, we defined it as an integer. So it's just, this is the zeroth term. So you keep incrementing. Is what allows you to get to the next term. So I start from 0, but you keep incrementing and incrementing like that. So we define the term as 1. This is just our initial definition. We say let the sum be 1 because the first term is 1. So we just say that let the initial sum be 1, then let the test be 0 because we keep on incrementing it. Then you're using sheet 2 now. I've already explained sheet 2. Then select the value in B1. Remember when I went to the when I went to the Excel, B1 is where X is. So go to B1, then put in X. So that means that the content of B1 should be what X signifies. This, this, okay. I think there's a question. Okay, yeah, ask your question. Samson, you can ask your question. Why is there ash? Okay, ash, thank you for that question. Ash is just to indicate that is is a floating point value. That is, it is not an integer. That's what the ash represents. So no, I is an integer, so it doesn't have floating point values. But in Visual Basic, instead of saying that, instead of say 1.0, we just put the hash there. We just put the hash there. So the hash is when you don't want to write the decimal fraction, the decimal parts of the definition. So thank you for that question. That's a very good question. So because this I is an integer, so it doesn't have point 0 there. It doesn't have point 0 because it's an integer. But we define this 10, define it as single, and single is a as decimal part. So instead of just putting the point, we just put hash. So this is single and this is single. So thank you for that question. Then this line is telling you that you should clear the content from A3 to C100. Let me go to Excel so that you can see what I'm saying. So it's telling you to clear it from A3. So A3 is here, then C1000. So it's saying that you should clear all of this. You should delete it. So if there was something, if there were some values there, you should delete all the values that is from A3 to C1003. Then the next line is that you should select cell A3, then you should run the iteration. The first thing is that, this is a do loop. Like I said in the previous class, a do loop is an infinite loop. It keeps on going on and on and on like that till infinity. The only time when it goes out of the loop is when a condition is satisfied. And it is that condition, this is the condition here. So we are saying that if sum is equal to test, then exit do. Remember I told you that test is the summation prior to the particular term you're using. So if sum is the summation of all this, then test is the summation from here to here, while sum is summation from here to here. So what it's saying is that if this summation, when you do this and you add it together, and when you do this and you add it together, if there is no difference, so that means that we are getting closer and closer to the exact value, because you are increasing the number of terms. So if the previous solution, which was this, is the same thing as the current solution, when you add the next term, then that means that you've arrived at your exact value. Then you should exit, you should leave the loop. So that's the condition. Then this is saying that at cell A3, you put in I. So I is the current term. Then offset by one column. So go to the next column and put in the term. Remember, term is, it will just evaluate if I is 1, if I is 0, term is 1. If I is 1, term is X. If I is 2, term is the highlighted equation. If I is 3, this is term is the highlighted equation. So you put in the term, you evaluate the term here, then you go to the next column. This represents row, while this represents column. So this said, go to the next column, then write the sum here. Then after that, go to the next row, you have a 1 here. Then offset the column by -2. So shift, what it's saying is that 1 minus 2. Let me go back to Excel so that you would understand better. So that offsets 1 minus 2. So there was offset 0, 1. So you are in A3, offset 0, 1. That means go to the next column. Offset 0, 1, go to the next column. So once you are done with that, the offset is 1 minus 2. So go to the next row, then offset by -2. So this 1, this 1, then this 2. So go to the, so it's going to go here. So on the next iteration, it's going to calculate the term value, it's going to calculate the sum value, then it's going to go to the next row and come here. It will write the next iteration, to write the term of the next iteration. It will calculate the sum, it will go to the next row, then it will offset by 2, 1 and 2. So we are simply, that's what we are simply doing here. So that's what this means. Then increment I. So go to the next step. So this is I is equal to 0, I is 1, I is 2, I is 3, I is 4, I is 5. Then it keeps going on and on like that. So what it's simply saying is that when I is 0, calculate the term here, then sum it. So here is just 1. So when I is 1, calculate calculate this, then sum it. When I is 2, calculate this, then sum it. When I is 3, calculate the term value, then sum it. When I is 4, calculate this, then sum it. You keep on incrementing, and the only time you stop is if this, when you calculate this summation that is highlighted, and when you calculate this, and the result is the same thing. So when sum is equal to test, then just exit. So that means that your precision or the error is, you are not adding more terms, doesn't make the calculated value more precise. So you should just leave the loop. Then after leaving the loop, it's going to write the exact value at the next column, at the next column. So the row is offset by 0, then the column is offset by 1. Then after that, you offset by another column, still on the same row, but another column. Then you find the exact value. So that's what the function is simply doing. So I've already run it. Let me go back to the Excel share. So like I said, we are using sheet 2. Yeah. So this is the exact code. This is the name of the subroutine. You can call it any name. So it doesn't matter. And okay, before I close on this, uh, let me go to this function. So this is the summation. So the sum, you're going to put it in test so that this summation will have the exact sum up to the current term, while this test is going to be missing the current term. That's why you have this. Then this is the main Maclaurin series. Let me go back to the note. This is the main Maclaurin series. So what this is saying is that, x raised to power of I. Remember, I is the current iteration divided by the factorial. So this is the function for the factorial. Remember when we wrote the first function in Excel VBA, we wrote our function to calculate the factorial. But fortunately, there is a function in Excel, and the name of the function is fact. So this function calculates the factorial. So if this is 2, it will calculate 2 factorial. So I'm just writing it for effect. So this is the function fact I. So if you have 4 here, so what this simply means is equal to 4 factorial. So that's what it simply means. And we are using this. So this is saying I should go to the application and you go to the worksheet, because you can only find this function or method at this location. So that's why we are calling this function. So in the previous example we did, in the first example actually, we wrote the function. This was the function to calculate the factorial. And this was how we calculated the factorial. I explained it to you because I keeps incrementing. So the first factorial is 1. The first factorial is 1. But at the second iteration, you have 2 here. So you have next factorial is 2. Then at the third iteration, this is 2, then this is 3. You have 6. And it keeps on going. This is 6 and this is 4. So you have 24. For this one, we calculated the factorial ourselves. But in this case, we don't want to do the factorial ourselves. We just want to use this function that Excel has, that will calculate the factorial for us. So basically, that's what this function actually does. So it's a subroutine, so you don't need to call it within Excel, just run it. Just press this run here. And when you run it and you go back to Excel, so in Excel, it's going to display the results for you. So at this point, is going to stop, because when it calculated the next term, which is 31, this and this were the same thing. So it stopped here. Then after that, it calculates the exact value. So when you compare the exact value, so this is the exact value, and this is the estimated value. And you can see that there is an error. So we are just talking about errors uh, in mathematical approximations. Okay, so enough with the coding now. So we are going to do some mathematics now, and we are actually moving to we are still within the same topic, but we are moving into Taylor series, because in the first class, remember I told you that Taylor series is Taylor series, the Euler's method we used, that's this particular Euler's method. This particular Euler's method is the first two terms of the Taylor series. So we got it from the Taylor series. And this is, so in the Euler's method, this is the Euler's function in which we're using to approximate our models in order to get the numerical solution. And we use the first two terms of this Taylor series. So the next time step is equal to the current time step. Then the differentiated function, then the step size delta t. So like I said, we happen to get the Euler's method from the Taylor series, and the Taylor series is an infinite series. So if you have a function and you have a function f of x and you want to calculate the next time step, that's fx plus 1, you can use the Taylor series to approximate it, and using more terms of the Taylor series is going to give you less errors and better approximation. So we are still within the same topic, but I want to give you a brief idea of what we want to do now. So if you have a function, let's say, I just want to tell you what we are doing now so that you can really be sure. Let's say we have a function. Uh, Let me call the function, I'm just giving an example now. Let's say the function is x squared. Let me just say 2x squared. So if you have this function, 2x squared, and you know that, okay, let's say that uh, x is equal to 1. Let me put it in equation form. And x is equal to 1. So you know you have this particular function, and you know the value of this function at x is equal to 1. So you know that 2x squared at x is equal to 1. So if we just calculate this, we know that is equal to 2. So what we want to do now is that we have this function, right? We know the function. Then we know the value of the function. At we know that this is our function. We know that at x is equal to 1. At x is equal to 1. We know that f of x. Know that f of x is equal to 2. If this is known, then you are asked that based on this information, find the value of the function. So based on this information, find the value of the function at x is equal to 2. So this is what we are doing now. This is just the summary of what we are doing now. Okay, I'm explaining it again. You have a function, and this is the function. And you know the value of the function at a particular steps, at a particular point. You know that the value of the function is 2 at x is equal to 1. Then based on this information, just using this information, find the value of the function at x is equal to 2. Of course, you might say that this is a very simple math problem. You can just say that to find the value of the function as x is equal to 2, just put 2 here, because here x is equal to 1, then here x is equal to 2. So when you do this, you're going to get 8. You can say that, okay, this is how to go about it. We are done. But what the question is actually saying is that what the question is actually saying is that using just this information, you know the function, and you know the value of the function at a particular value. So the question is to get the value of the function at another step size. So you know the value of the function at x is equal to 1, then get the value of the function at x is equal to 2 based on this information you have. So it's based on the fact that you know the value of the function at one particular step size, then estimate or predict the value of the function at another step size. Though you can do it this way and say that, okay, but what we want to do is just based on this information. For instance, there are some, you may not be able to calculate, we know that this is the true value. This is the true value because we know how to do maths. We're already good in maths. So we know that this is the way to go about it. When x is equal to 2, you just put in 2 here and you calculate it. But the question is saying that just based on this information only, you know the value at x is equal to 1 is 2 of this function. Then what is the value, just based on this information, find the value at x is equal to 2. So that's what we are going to be doing now. And we're going to use Taylor series to do that, to approximate or to predict the value of a function. When we know the value at one step size, we use Taylor series based on that information to get the value of the function at the next step size. So this is the question. And we had to use 0 through 4th order Taylor series expansion to approximate this particular function. So we know that when x is equal to 0, so we are given that from x is equal to 0, then this is the step size. We represent the t as the step size. And this is the formula for Taylor series. Taylor series is an infinite series. And the reason we are going to use Taylor series is that, we want to calculate the value of the function at the next step size. So this is like the next step size. So this is the current, this is at the current step. This is at the current step. So based on this information, calculate the value of the function at the next step size. And this is what we are going to be doing. And we are doing that because we want to look at the error, we want to observe the error. And Taylor series is an infinite series. Yeah, we did it. This is the 0th term, this is the first term, the second term, the third term, and this is you can keep on going on and on like that. So it's till infinity. So this is the last term. So we're going to be using Taylor series for that. Simply, when you know the value of a function at a current step size, based on that information only, you want to find the value of the function at the next step size. So I have less than 1 minute. We have a lot to do today, actually, because um, I'm just on page 5 and we are going to page 17. So we keep rejoining